This podcast is sponsored by Lightstep. Lightstep delivers confidence at scale for those who develop, operate, and rely upon today's powerful software applications. Answer questions and diagnose 100% of anomalies, spanning mobile, monoliths, and microservices across every service in real time. Visit lightstep.com.
Hello and welcome to the InfoQ podcast. I'm Wes Reisz, your host. In addition to hosting the InfoQ podcast, I chair the QCon software conferences in London, San Francisco, and New York. Today's podcast kind of originates from a talk that was done at QCon London. That talk was entitled The Modern Operating System. In the Modern Operating System, Justin Cormack, who is our guest today, spoke a lot about topics like Unikernels, LinuxKit, eBPF, and Cilium, on how we're actually decomposing the last modern monolith, the operating system. So in today's podcast, we're going to dive into some of those topics and talk a bit more. Justin is at Docker today. His past work has been with security, containers, unikernels. Justin, welcome to the InfoQ podcast.
Thanks for having me on.
So today you're a system engineer at Docker. Prior to that, you were with Anil Metapafetti at Unikernel Systems that was purchased by Docker, right?
Yeah, that was coming up for 3 years ago now.
Are you continuing that same work at Docker, still working unikernels, or like we talked in the introduction, security and containers, have you kind of spread out a little bit more?
Yeah, I kind of spread out a lot more into the bottom of the stack and how it relates. And a lot of the driving factors around the work we were doing on unikernels was around security, and that's been my focus recently. But there's a lot of infrastructure around building up towards work on unikernels, work related to some of that similar thinking. I worked on LinuxKit, which was very much driven by the same kind of philosophy as unikernels, even though it's actually in many ways more traditional and more approachable. We're still kind of trying to understand the drivers for adoption around unikernels, and there's a lot of interesting work going on in that space still, but it's not a production thing that we're shipping at Docker at the moment.
How's LinuxKit been going? What's the adoption you're seeing? What's the community response? How's the project going?
It's actually been really interesting. I mean, we built it for our own internal purposes, but we realized before we released it as an open source project, it needed to be useful for other people to get contributions. And so that was just over a year ago now. And it's a very different project. It's kind of, in some ways, some of the same philosophy as CoreOS Linux originally did and some of those things, but it's still quite radically different.
What about adoption?
We had this initial enthusiasm about adoption, and it's been growing gradually, and it's been really exciting recently. We've had new people adopting it. We're hoping to have more talk about it soon, but we've got people in big cloud providers using it. We've big service providers. We've had contributions from people like Intel, Oracle, Cloudflare, and so on. So that it's really finding its home in people's tech stacks, which is really quite exciting. And we've had a growing number of contributors and contributions, and people are starting to understand what it's about. I still find I have to go and talk about it quite a lot because it is a different approach and it's a different way of thinking about how you use Linux.
What do you mean by that?
Very much as an appliance-led way of thinking rather than the kind of workstation way of thinking. You know, those kind of changes in how you use your tools are things that don't just happen overnight. People are used to one way of doing things, but people are finding little niches where it makes sense and expanding out into other areas.
So LinuxKit, it's a toolkit for kind of building immutable Linux distributions where you can kind of like compose the operating system with things you want to do. Is that right?
Yeah, that's right.
You said, for example, you've got some large cloud providers. Can you walk through maybe one of the use cases to give someone an idea of one of the use cases that someone's using LinuxKit for?
It's still quite a mix, but if you have a part of your pipeline that just is something that you're running that is providing a single service, such as a image transformation pipeline or something like that, which is fairly compute heavy, does a bunch of work on an ongoing way that you need to scale up and scale down, and you want to just do that in a VM because it's a big scale thing, just building LinuxKit VMs to do that, it's a really straightforward use case. You just build it, deploy it, let it run, scale up and down as you need. It's very much the container philosophy, but for whole VMs or for whole bare metal systems. We have people using it on bare metal. We've got a whole bunch of people using it for embedded IoT type systems as well. So there's that whole kind of edge use case there, which is a growing use case in edge as well.
And so does a hypervisor just see it so much as just a VM and just treats it like a VM?
Yeah, most people use a VM. We actually have a lot of people using LinuxKit on bare metal though as well, because it doesn't need a VM. And one of the things that was really interesting when it came out was the amount of people we had using it on bare metal, not VMs, because the VM use case was our original use case. But it turns out that bare metal automation has really made a lot of progress in the last 5 years or so, and you can deploy stuff onto bare metal really quite straightforwardly and easily, and you don't necessarily need to use VMs to get that kind of cloud agility. And we've seen that with AWS launching bare metal instances, and as well as other smaller cloud providers now, but like Packet, who've always done that. But it's a real change that bare metal is not this kind of magic thing that's difficult to deploy to anymore. It's actually, there's this whole automation stack around bare metal as well. One of the things generally with containers is that people are saying, why am I running VMs when I'm just using them to run containers as well? It's the same question about, are VMs useful for every use case? Maybe not.
Absolutely. It's super cool work. So the main thing that I really wanted to dive into in this podcast is this notion of decomposing the last true monolith, the operating system. You did a talk at KubeCon London that I believe the title was The Modern Operating System. And it basically went about this idea that we've had an operating system and a certain kind of mindset for a long time. And we're starting to kind of rethink what it means to have an operating system. And there's a lot of tools and technology that have been coming out to kind of enable that, such as unikernels that you talked about. And I think there's the example of SQL Server being deployed on basically a unikernel for Linux. So basically, I wanted to dive in and just talk a bit about some of the technologies, things like eBPF, things like Cilium, things like unikernels, and talk about that in general. So let's start off with just basically, why now? Why have we had the idea of an operating system, what it currently is in its current incarnation? Why are we now starting to rethink it?
I think the kind of history of why we get to what we have now, I think really the operating system, particularly the Unix operating system as we think of it now, really came from and is very much unchanged since the sort of Sun workstations of the 90s, when that was people's first exposure to, in many cases, to Unix as a thing. It was an operating system, an environment designed for developers, and it was incredibly exciting. And that's what led to people, like Linus wanting to build Linux so he could have his own Unix workstation. And our kind of idea of really everything, that the Linux distributions were designed to replicate that experience. And it obviously went from proprietary to open source over that period. But the design is very recognizable. I mean, if you put someone now down in front of a workstation from the 90s, they would know how to use it. Many of the commands would be the same. And we haven't really rethought that design when everything else has changed. So what we changed was how we deliver software. The big change has been around speed of delivery, build pipelines, automation around delivery, but automation around the OS and delivery around the OS has changed much more slowly than anything else. And so we're kind of catching up to try and bring everything along into that kind of world that we have for all the rest of our software.
Yeah, totally.
Operating systems are still written as large monoliths written in C by kind of niche teams. And that's not how we write any other software. It used to be how we wrote pretty much every piece of software. And now it's just the operating system that's being written like that. Coming back to LinuxKit, one of the things that was one of the design requirements for LinuxKit was that you should be able to build it on your laptop in a minute and then deploy it like any other piece of software. You can't really do that with the big monolithic enterprise Linux or something, something like that. You don't build and deploy a new custom version of that from scratch in a minute from your laptop. It's a very much more complicated process. So that's kind of where we came from and where those things were from.
The other thing you kind of talked about in your talk was that hardware and performance requirements really changed too.
And the real step change that really became noticeable was when we went from 1 gigabit Ethernet to 10 gigabit Ethernet and above. Because unlike most things that in computing that just, clock speeds go up bit by bit, and you get a few more cores, there's a gradual change, you get more RAM, and software gradually sort of fills into the extra headroom it's got. Ethernet's always had this process of going up in these steps of times 10 factors, much less frequently. And gigabit Ethernet was something that we'd had for a long time, had become kind of normal. And the performance requirements from the CPU to drive it were not that great. When we got to 10 gig Ethernet, it suddenly changed really quite dramatically. Most software couldn't really drive it at anything approaching line rate at all. People couldn't really make use of it. And the networking really went quite rapidly after 10 gig into 40 gig, and we would have 100 gig now, but people are still having difficulty driving that. And at the same time, the effects were kind of less immediately noticeable, but it coming along more now, was the same thing happened with storage. We went from hard drives to SSD, and suddenly we had something that had kind of sane latency, and you could use it in different ways. And again, the software architecture wasn't really built for that. So you had a kind of system in kernels around networking and storage that was built around optimizing for slow hardware, optimizing for a set of kernel interfaces that just really didn't have the performance for the new hardware we had.
Okay, so in your talk in QCon London, you quoted Ken Batcher, and you said a supercomputer is a device for turning compute-bound problems into I/O-bound problems. As you're sitting here talking about 10 gigabit Ethernet, the skeptics are out there screaming CAP theorem, and you can have 10 gigabit, you can have 100 gigabit, but you're still going to have network partitions. So how is it that you can ever trust a distributed operating system?
I think we've realized that trusting a distributed operating system is difficult, but we're building distributed systems not because we want to, but because we have to, because we want, number one, we want reliability. And number two, we're trying to solve problems that are just too big to fit on one computer. And those two went hand in hand with the kind of revolution towards scale out rather than scale up. We stopped buying bigger and bigger computers and started buying smaller computers because it was more cost effective.
So maybe it's just my ignorance here, but when we're talking service-to-service communication, we're passing either a binary protocol or JSON around, and you want to have reliability and fault tolerance on the system there. I can see that. But at the operating system level, there's things that are happening with memory and user space that you just can't distribute, can you?
Yeah, I think that there's always been a dream of a sort of transparent distributed systems layer that sits as an operating system above everything. And that dream doesn't go away. The distributed operating system isn't a reality yet. We're still in a state where you still have to think about, is this operation local or remote? What's the latency of it? What do I do when it fails? That's still a dream that a lot of people are working on, and a lot of people are trying to build things that are more like an operating system again. And distributed operating system definitely isn't dead. Mesos has DCOS, they've put operating system in the title of their software, and more people are thinking about that. There are definitely people who are building things they consider to be distributed operating systems now, but they're still mostly quite early. You have to build the reliability and the retry and the fault tolerance into that so it becomes invisible. And obviously, there are CAP theorem issues, so you have to decide what the semantics are. Those semantics matter, and so the work you do has to either be suitable to be eventually consistent, or you have to accept that things are going to stop happening, and we're getting better at understanding what those constraints are. We've got systems like Kubernetes where we've got a model that works for many applications that is arguably a part of an operating system. It runs processes in a distributed way and supports operations between them. It's arguably an incomplete operating system because it doesn't have all the pieces you need to build it up. We're getting to the point where we're having things that people are going to start calling distributed operating systems again, and I think that's good, but people are kind of wary because they know what the pitfalls are and they understand the pitfalls, because we have been through some of this in the past as well.
Sure. So where we are today, and correct me if I'm wrong, is the idea of slicing all the different pieces you need for an operating system. The idea with like containers, putting what you need, all the drivers, everything into this one particular package that you deploy, but taking that now down into the operating system. So like if you're doing networking or TCP/IP stuff, you put that actually into the box, the container with the application, like for Unikernel, and then deploy that. That's where we are today when we're talking about decomposing the monolith. Is that right?
Yeah, I think that at the moment you can definitely go that far, and some people do and some people don't go that way. I think what's happened is that at the moment people are using a kind of hybrid model, and I think that that's really what the XDP work in Linux, Express Data Path work, which has been the kind of cutting edge around what the eBPF world has been delivering in Linux, and the kind of what we've been seeing recently has been about.
Okay, you said XDP. What is Express Data Path?
Express Data Path is a packet processing layer for Linux, which lets you run eBPF programs, which are, fast in-kernel, compiled, safe programs that can do things like packet filtering, encapsulation, decapsulation, and so on. And then XDP then lets you also feed those packets either into the Linux TCP stack in kernel or into user space fast as well. And so this is a kind of hybrid where you can not totally redo everything from scratch, but you can use parts of the kernel, and parts of the stuff you can kind of build it from scratch yourself. So I was trying to build an incremental approach to these kinds of things rather than just saying, I mean, the unikernels approach was quite drastic, and we said, let's build everything from scratch. Let's build a new stack that's just a library that you can build into your application that does everything. That requires more work because you have to build more infrastructure. And so there's this kind of hybrid path we're seeing now of just building with performance, doing partial in kernel, partial in user space, partial reuse of existing software.
Okay, let's come back to the hybrid approach in just a second. When you were talking about XDP, you said eBPF is a fast in-kernel compiled program. Can you elaborate a bit on that?
So eBPF is a programming language in the Linux kernel. It came out of the Berkeley packet filter, which has been around for a long time from the BSDs, which was just a very simple processing language for filtering packets in the kernel. But eBPF added an extended set of instructions so you can write much more complicated programs, an extended API that can see more in-kernel information about network packets, and also allowed it to be applied to other things that are not network packets. It added a just-in-time compiler, and it added a path for communicating with user space. So you could do things like summarizing statistics information about what was going through the network or the disk or something like that inside the kernel into user space with great performance. So originally, a lot of it was around just performance monitoring and working out, passing information about what's going on in the kernel back to user space. And then it started growing this whole network stack, lets you do fast packet processing, lets you actually write real algorithms on packets in the kernel and actually modify, create, and pass packets around between programs and user space, stuff that's coming in on the wire, and so on. If you consider what something like a system with a bunch of containers on, for example, containers each one has its own networking stack because it's a container, it's got an isolated view of the network. But obviously what you really want to do is switch traffic between containers if they're talking on the same host and send stuff externally to different hosts. And potentially you want to encapsulate packets in some sort of tunneling protocol. Maybe you want to encrypt them and so on. So eBPF is actually really good at doing this. And this is where the kind of Cilium project started, for example, as a way of processing container packets really fast. And they've been, cutting edge users of all this technology in the kernel.
How approachable is the idea of eBPF? I mean, you talked kind of earlier about how the operating system was kind of this group set aside that was doing this and kind of was different from a lot of other development that was going on. Is eBPF approachable for the C# developer, the Java developer that's out there, or is this still kind of a system level, low level packet filtering kind of world?
It's a kind of weird language in some ways. It's got a weird set of APIs because it sits inside the kernel, and you kind of have to understand things like kernel data structures a bit, which is not something that's in most people's normal everyday work. There's a toolchain, an LVM-based toolchain for it, so you can compile C. Cloudflare actually have a really nice Lua-based eBPF toolchain based on LuaJIT, which is actually quite approachable. So you can write programs in Lua, which we compile to eBPF programs. So that's a kind of nicer scripting language if you don't want to play around with C. It's kind of nice because you can share code between the user space part and the kernel's part. But it's definitely not your everyday programming language, and it's kind of restrictive. And partly because it's partly restrictive just because the actual language is a very limited language, in order that it can be verified to be safe to run in the kernel. And so there's a validator that will go through and check your program, for example, terminates and doesn't have infinite loops in it, things like that. Until recently, it didn't even have things like function calls, though those were introduced recently. So it's become a little bit less restrictive, but it's still definitely a peculiar programming language in a peculiar programming environment. But it's kind of fun. Yeah, it's definitely not something that a lot of people have played with yet, but I think more and more when I'm talking to people who I know, they've started trying things out, and I think it's definitely a growing area. There's much better tutorials and so on than there used to be.
What I think's neat about it, and like LinuxKit and things, is that what people are doing now is they're building on top of this work to be able to create things that are more approachable for folks. And one you just mentioned a few minutes ago, Cilium. And that Cilium, as I understand it, and please correct me if I'm wrong, but It's a service mesh, but it's a service mesh that allows this kind of interoperability of services that operates in kernel space. Is that right?
Yeah, I mean, it's conceptually very similar to Envoy in many ways, but it runs in kernel space rather than user space.
Real quick, Envoy is the sidecar model for service mesh produced by Lyft that basically deploys service and it has a container next to it. And your service talks to kind of local hosts. So it talks to the Envoy instance, and then Envoy knows how to discover, talk, track, observe all the other services that are happening in it. So it's similar to that, except rather than in user space or going back and forth between kernel and user space, it stays solely in kernel space with the instance, right?
Yeah, and it's interesting because it can do things that kind of unexpected. So if two containers want to talk to each other and they're talking to each other over the network, it can actually just connect the flow of the TCP flow from one to the other directly, effectively through a Unix socket rather than through the TCP stack, because it knows they're on the same machine and it's in the kernel, and the kernel can do things like that. They can actually get more performance than actually without it, which is really kind of strange.
A lot of times when we talk about service meshes, we're talking about work that's done at both a data layer and a control layer. We even have Linkerd2, which just merged from Conduit, implementing both in different languages, Rust for the data layer and then Go for the control layer. They just do different things, so it kind of makes sense to use the language that helps you be more effective for the given use case. So I get how operating in the kernel can be do super interesting things in the data layer, the layer 4 stuff, but in the control layer, the layer 7 stuff, like some of the proxying for binary protocols or things like that, it's not really able to do what Linkerd or an Istio or an Envoy or something else that I'm sure I'm missing can really do there, can it?
It's difficult to do directly all the kind of complicated layer 7 and application layer processing in kernel, because the kernel deals with packets rather than streams to a large extent, and it's not the easiest thing to write.
All right, so it's not like a one-to-one comparison with something like Envoy or Istio when it comes to a service mesh.
There's two things that service mesh give you. One is kind of layer 4 type data layer, but they also give you often a kind of layer 7 type. So converting, say, HTTP 2 to HTTP 1 because they didn't support HTTP 2, or proxying gRPC into JSON and things like that. And that stuff's not really in the kind of design space of stuff you can sanely do in the kernel, or would we even want to do in the kernel. Those parts aren't the high performance piece, particularly because those applications are not massively performance critical. But you can take your native fast gRPC applications and run everything through Cilium.
Okay, I got it.
The other thing that's interesting is that Linux actually added support for TLS in kernel, which was a kind of weird one of these things, because for a long time people were saying, why would you ever want to do TLS inside the kernel? It's a slightly confusing to say it's in kernel because it's partly in kernel. So the TLS handshake takes place in user space, and then you hand over the connection to the kernel, which then handles the encryption piece of it. And so Cilium can do things like it can see unencrypted traffic in the kernel and actually inspect it there and make decisions based on that. So there are interesting kinds of things around transparently adding encryption potentially in kernel, things like that you can do. It's a lot of the data plane stuff that you expect from a modern service mesh, not the control plane, and you're not doing in-kernel acceleration of some of the layer 7 stuff. But the rest of it turns out you can do really kind of nicely.
What about the story around observability and specifically logging down into the lower level, you call bottom of the stack type information? Being at layer 4, what do you get that you might not get from a service mesh that operates kind of at a higher tier? Or do you?
I don't think from the observability point of view, it's actually that different. And I think one of the interesting things about eBPF was that a lot of it came out of the work that Brendan Gregg's team did at Netflix around taking all the tooling that they had for Solaris and dtrace and turning it into observability tools for Linux. And so they've done an amazing job of making the Linux kernel so much more observable than it used to be. And they have a really interesting, set of tools for observability that are based on eBPF and which are very high performance and actually let you extract a lot more data than you would be able to with traditional tooling. And I think a lot of the people who are doing monitoring and observability on Linux, I certainly know the ones in the security space are doing that, is switching to using eBPF because it's just so much more performant than trying to observe what's happening from user space. Yeah, a lot of the tools like Sysdig and so on are moving to eBPF-based models for getting information and understanding actually what's going on in applications. Because the kernel actually sees most of the interesting things that applications do, like writing network packets and forking processes, running binaries, all the things that really go on. Everything except computation is actually a call into the kernel. And so that kind of set of observability tooling, which was all built for high performance observability, is actually a pretty flexible toolkit that is probably what you're going to use anyway.
So what's next? We talked about XDP, we talked about EPF, a little bit about unikernels. What's next in the world of decomposing the monolith or the operating system?
Well, I think that as well as eBPF doing everything in the kernel, there was always the other choice of do everything in user space. The choice is never leave the kernel or never enter the kernel.
So it's the context switching between user space and kernel that causes the delay. If you stay on one side or the other, you can improve the performance.
Yeah, you don't want to context switch, you don't want to copy data, you don't want to go through two separate sets of APIs and so on. We've seen a lot of stuff, particularly built around DPDK. GitHub recently released their layer for load balancer, which is a really interesting thing, which is based on DPDK.
What is DPDK? I'm not familiar.
DPDK is a Linux Foundation project originally started by Intel, but now cross-platform for basically user space drivers for network cards. So that's been one of the primary user space paths for developing stuff.
So real quick, that would be like a kernel bypass library for networking kind of, is that kind of the idea?
Yeah. So it has a user space driver that talks to network cards directly, obviously focused on 10 gig plus networking. Originally it was Intel, but it now supports pretty much everything. That was basically one of the main routes to doing everything in user space. What we've seen with the recent, in Linux 4.18, the recent XDP patches, is there's now a kind of hybrid path, which lets you do fast transfer straight from the kernel into user space. So you can do a kind of hybrid. You can do some eBPF code and then do everything else in user space and potentially pass some stuff into the kernel TCP stack as well if you want, but you can do most of the work in user space. Linux has always had a few kind of ways of passing packets directly, bypassing the kernel stack, but this is one that actually promises to be really fast.
What's it called?
It's the AFXDP socket. It's kind of newer version of the old packet socket format, but it has zero copy support, and it basically gets stuff straight into a ring buffer you can process in user space. And it works with pretty much all network cards. And so I think we may see more people actually using that rather than DPDK, perhaps, because it's potentially easier to use. And then you can use a hybrid of some eBPF and some user space processing as well. So I think that's been quite an interesting development that's been sort of promised for a while and finally got merged in 4.18. So I think that's kind of quite exciting.
All right. So one last thing. In November here at QCon San Francisco, you're going to be running an operating system track kind of based on some of these things. What are you hoping to put in this track? I know this isn't a commitment that these are the things that are going to be there because it's still a little bit early. But what are you specifically looking at to talk about in this OS track?
Well, as we're talking about eBPF, we're definitely going to have a deep dive on eBPF. We should be announcing the speaker shortly. And this is something that everyone's really excited by. I know a lot of people are working on this. It's really becoming really accessible, and that's really important. Talking about changes in hardware, we've got Alan, who works on Memcache, is going to be talking about working with non-volatile RAM and the new fast things in the storage space, because storage has been something that's been a little bit behind networking in these changes, and I think, but it's becoming really important because we're moving towards an era where you're going to have flash memory on the memory bus in large quantities, probably preview now, so early next year. I mean, it's one of these things been promised for quite a while, but it's finally starting to ship, and we're going to get large-scale, fast, random access flash memory, and that's really going to change architecturally how we do things. It's a big change, so there'll be a talk on that. One thing I talked about quite a bit at my London talk, and we will probably have a talk on it again, is the whole space of emulation, which I think is really a fascinating area. So we have this whole thing that we have these performance bits that are kind of bypassing a lot of the kernel traditional stack. But the Linux kernel ABI is really the one stable thing about Linux that's really important. And we have a huge number of programs that have been written for that. And, it's going to be incredibly important, even if a lot of code ends up, ripping up the kernel and using its own TCP stack and so on. A huge amount of code has been written that uses the Linux stack. And there are lots of reasons why you actually might want to run this in an environment that actually isn't a traditional Linux. One of the massive things we've seen has been the Microsoft effort to have Linux running on Windows. And they've been doing an incredible job on this. I mean, this is something that emulated Linux happened back in the 90s on NetBSD and FreeBSD and Solaris. But Microsoft have actually put a huge amount of engineering effort into this. And they're getting to the point where not only do most applications run, they're starting to fill in the difficult bits, like, running things like containers and C groups and so on are starting to be implemented. And it's really becoming a fully fledged way of running Linux programs without Linux at all. And just a couple of months ago, we saw Google release gvisor, which is another emulation thing. This is based on what they used for Google App Engine. So Google App Engine uses a version of this internally to sandbox the code that you run. They don't want to run like any Linux code just untrusted on their machines in App Engine because it's a shared environment that they run in. They don't want to run a VM per machine. So they run your code using gvisor. And the release version of gvisor has an emulated TCP stack. It doesn't use Linux TCP stack. It has a TCP stack written entirely in Go, which comes from the Fuchsia operating system that they're developing for mobile. So it's a kind of interesting thing. Again, they're using emulation for security reasons this time. And so you're getting this situation where you've got this whole layer of emulation around running Linux binaries that are not Linux, on something that's not Linux. And potentially that can be a way of running stuff on, new operating systems we develop or on Unikernels and so on. You can potentially use some of this kind of emulation technology to run existing applications. So there's a really kind of interesting space around that. The Windows stuff is interesting because originally it was just to build as a tool for developers to run some compile stuff that they're in a familiar environment. But that team got moved into the Windows Server team, and it's now shipping on Windows Server. It's now moving towards a way of running Linux code in production, not on Linux, which is a really interesting change in how we treat operating systems.
I remember when we first started talking about Amazon and cloud, we talked about the undifferentiated heavy lifting being able to be removed. Now we're moving undifferentiated heavy lifting down into the operating system with decomposing the operating system. So very cool. So if you want to learn more about decomposing the operating system and the way the new modern operating system will be shaped, make sure you check out Justin's track at QCon San Francisco here November 5th through 7th. Justin, thanks for taking time to chat with us.
Thanks very much.